Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Now let's move toward sample problem 5.1 and we will discuss all the things that we discussed earlier in this lecture. So you can see this is a timber beam and loading is also shown. Here you have been asked to draw the shear force and bending moment diagram and determine the maximum normal stress due to bending. So you can see this is the beam, timber beam, and this is cross section of the beam is given, height is 250 and width is 80 mm. There is a point A and the loading on point A is a concentrated load of 20 kilonewton. At point B it is a simply supported or pin supported. At point C there is a concentrated load of 40 kilonewton and at point D there is a rolling force. Rolling support. So if I draw the beam like that, so this is a point A. At point A there is a 20 kilonewton force. Clear? At point, this is a point B. So at point B there will be a normal force as well as horizontal force. So we ignore the horizontal force because there is no other horizontal force acting along x direction or in this axis. So it will be 0. So only the reaction force will at point B is RB. At point C, this is a point C, and at point C there is a force of 40 kilonewton. And at point D there is a rolling force, and that if you remove the rolling support, so there will be a reaction at point D which is RD. All the distance are given from point A till point B. It is 2.5 kilometer. From point B to point C this is 3 meter, and from point C to point D is 2 meter. So this problem can be solved by using two methods. First, I will use a simple method in order to show you a clear understanding that how you will able to determine the shear force and bending moment in this case. Similarly, in next problem we will solve the same type of problem by using another method that will depend on the in that problem we will show you that shear force and bending moment varies along the length of beam. Here it also varies, but I will not consider this in this problem. So let's start its solution. So first of all, the first step is to find out the reaction force RB and RD. So how you will find? So you will have equation sum of all forces along y direction is equal to 0 and upward is taken as positive. So you can see one force is 20 kilonewton that is acting downward, so it is minus. There is a reaction force at point B that is taken upward, that is RB, plus there is a force, minus, there will be a minus force because this 40 kilonewton is acting downward. So minus 40 plus RD which is acting upward. So their sum must be equal to 0. So from this equation we get RB plus RD is equal to 60. So this is the first equation because minus 40, minus 20, minus 60, and when it moves toward the right side it will be 60. Now the second equation that we will use is sum of all moment you can take at either point B or point D. So let's take at point D is equal to 0. So one force that is producing moment is 20 and it is perpendicular distance is 2, 2.5, 4.5 and this 3, 7.5. So 20 into 7.5. Now we assume that counterclockwise movement is taken as positive. So you can see this 20 kilonewton is producing a counterclockwise rotation, that is why it is positive. Now this RB force, this RB is unknown and perpendicular distance is 5 meter from point D. Clear? So RB is producing clockwise rotation. So that is minus RB into 5. And the third force that is producing movement in counterclockwise is 40 kilonewton. So plus 40 into 2 perpendicular distance. Their sum must be equal to 0. So if you calculate that you will find out the reaction force will be, so let me calculate as 5 RB is equal to 4 into, it is 80, this term is 80 and this 5 RB is moved toward the right side of the beam. Let me open the calculator, that is 20 into 7.5 will give you 150. So this is 150. So 150 plus 80 will give you 230. So 230. So 5 RB is equal to 230. So RB will be equal to 230 over 5. And that is equal to 166. Okay. So let me check it again. This minus 20 plus RB minus 40 plus RD is equal to 0. So their sum must be equal to 0. Now moment at point D. So 20 into perpendicular distance is 7.5 minus RB into 5 plus 40 into this perpendicular distance 2 is equal to 0. So let me check it also. So reaction force is 20. Let me calculate it. Okay, so let me erase something from here. This pen use. If you divide 230 by 50, sorry, it gives you 46. That this is 46 kilonewton. Now you know RB, so you will put over here. So RD will be equal to 60 minus 46. That will be equal to minus 60 minus 46. That will be 40 kilonewton. So this is how you find out the reaction forces at point D and point B. So let me clean these things. I will show you. Erase all. It's not easy. Okay. This was a let me check it why it's not working. So basically that was 46 kilonewton and RD was 14 kilonewton. They are the steps. So treating entire beam as a rigid body, determine the reaction forces, and we did the same. We first find out the reaction forces, then the second step is section the beam at a point near support and load application point. So this point is very important to understand. So first of all, you can see there is a point load. So you have to section near this point load. And this distance must be taken very small, negligible distance. So again, section the beam at a point near the support and load application point. So this is a load application point, so you can section it over here. There is support, so you can section closer to the load, just before this support. You can take the let this is 2. You can take the section just after this support, so that will be 3. Again, you can take the reaction force at you can take the section before the load 4, and you can take the section at just after the load, and again before this support 6. So you can see that you can take 6 different sections of the beam in order to find out the shear force and bending moment diagram. So when you find out the shear force and bending moment in this section, you will plot them on shear force and bending moment diagram distribution, and from that diagrams you will identify the maximum shear as well as the maximum bending moment. So let's solve this problem. And how you will, when you get the maximum bending moment, so definitely you will apply the sigma m is equal to mc divided by I, maximum bending stress, and this is known as flexure formula that is used to determine out the maximum bending stress. So this is the solution of the problem, sample problem 1. So you have seen that this is point A, this is point B, reaction force is 46 kilonewton, this is point C 40 kilonewton, and this is point D 14 kilonewton. Here reaction force is 46, not 40 kilonewton, and RD is 14 kilonewton. So again, treating the entire beam as a rigid body, and we want to find the reaction forces, and we did in the previous slide, and we calculated RB is equal to 46 kilonewton and RD is 14 kilonewton by using the equilibrium equation. After that, now we will have this beam. The total length is 7.5 mm, and the length distance between A and B is given 2.5, from B to C 3, and from C to D it is 2 meter. That is given. Now you have to take the section just after the application of point load. So at point A you can see there is a point load, so you can take section just after the application of load. So this is section 1. Now the distance between point A and section 1 is assumed to be very small. This x or this distance is assumed to be very small, such that point 1 A is or point 1 approaches to A. So we take the section of beam, so we this is point A. On point A 20 kilonewton is applied. So if you section it, so there will be a shear force that is acting downward, and there will be a reaction movement. Clear? So this is point A. In order to find out this shear force, so we will use sum of all forces along y direction is 0 and upward is positive. So now you can see that only one force that is acting downward, so that is minus 20, and there is a reaction shears minus V, their sum must be equal to 0. So V will be equal to minus 20 kilonewton. So it means that at this point 1, the shear force is same as at point A. And bending moment, this M, this is point 1, so moment about point 1 must be equal to 0. So at point 1 there is external moment acting as M1, clear, and plus the moment produced due to this load or this load, 20. So as this distance is taken as very small, so it means this distance is approximately equal to 0. So it means there will be no moment. So M1 will be, or this reaction moment, let me erase this. This reaction moment must be equal to 0. So moment at point 1 or section 1 will be equal to 0, because only reaction force is M and M2, and this reaction force will be, this reaction moment will be equal to this moment. But since the distance is taken as very small, so we can say that this moment is 0. Now you can also take section before the application of this point load, just before, and you can take it, let's say this is at section 2. Now distance of this section 2 from point A is assumed to be 2.5 meter, which is exactly the same point, but we assume that point 2 or section 2 is just before the point B, or you can say it will be on the left side of the point B, just before point B. So we will find out the shear force and bending moment for point B. So you can see this, at point A the 20 kilonewton load is given. So before point B, so if you cut it, so there will be reaction at point 2, which is V2, and reaction force M2. So again, if you apply the sum of all force along y direction is equal to 0, so you can see only force 20 kilonewton, that is minus 20, and this is minus V2 is equal to 0. So V2 is equal to minus 20 kilonewton, which is same as V1. Means that after point A and before point B, the shear force is constant. Clear? Now at point 2, you can see that at point 2, just before point 2, so sum of all moment about point 2 is equal to 0, and counterclockwise is positive. So you can see now that this is the diagram, and this M2 will be equal to, there is a moment M2, and there is a moment produced due to this load, this 20 kilonewton into perpendicular distance, and that is taken as 2.5. So 20 into 2.5, and it is also counterclockwise, so 20 into 2.5, that is equal to moment. So moment will be equal to M2 will be equal to 20 into 2.5 will yield you 50. 50 kilonewton into meter, but it's minus 20, that is 50. Okay, so moment at point 2 is now minus 50 kilonewton and meter. So you can see that the shear stress is constant, but now the moment is not constant. At point 1 the moment was 0, and at point 2 now the moment is minus 50 kilonewton. Similarly, you can also find out at point just after, let me solve it as well at point C. So at point 3, so point 3 is just after the point B on the right side, and this distance after the point B where you have taken the section 3 is very small, means it approaches to point B. Clear? So we will find the shear force. This is the equation. So this is 20, this is 46 kilonewton, this distance is 2.5, and this distance is approximately from this point to this is approximately 0. So you can find out the reaction forces sum of all forces along y direction must be equal to 0. So now you can see there is one force minus 20 kilonewton, other one is plus 46, and other one is minus V3. Their sum must be equal to 0. So V3 will be equal to 26 kilonewton. So from this we conclude that this actually point 2, section 2 and section 3 are very closer to point 3, and we assume that this distance is very small, that it is assumed that it lies at point B. So now there are two shear forces, one is 2 which is minus 20 kilonewton, and one is V3 which is 26 kilonewton. So it means that at this point B on the left side, the shear force was minus 20 kilonewton, but now after slightly moving from point B, the shear force is 26 kilonewton. And you can also find out the moment 3, and this moment 3 will be what? This will be the same as M2. which is minus 50 kilonewton. Because why? Because this distance is very small. Clear? That is approximately. So this force is not producing any shear. Only 20 into 46, 2.5 force is acting, 20 into 25. So M3 here will be also minus 50 kilonewton into meter. So you can again, now you have to solve at point C by assuming that C at point 4, and this point 4 is before the application of this point load, which is at point C. So you have to assume that this distance is very small. It means the distance of distance of section 4 from point A is now 5.5, but it will be to the left. And similarly, you can take the section at point 5 and you can solve it point 6. I will remove all this working and we'll see. Okay. So now you can see that this was the V1, which is minus 20 kilonewton, and M1 was 0, because this distance is very small and equal to or approximately equal to 0. So 20 into perpendicular distance, which is 0, is equal to 0. So V1 is equal to 0, M1 is equal to 0. Now at point 2, we have find out that V2 is actually this minus 20 that I have done a little bit earlier, and M2 is minus 50 kilonewton. And at V3, now the shear force is changing to 26, and I have also done that. And at point 3, M3 is again the same as M2, minus 50 kilonewton. And we similarly you can find out V4, M4, V5, M5, and V6 and M6. So now if you take this at point 6, so sum of all the force must be equal to 0. So 20 plus minus 20 plus 46 is 26, and again this is minus 14. So that will be minus 14. So V6 will be minus 14, and shear force is 0. Now we will plot it in order to get the shear force and bending moment diagram. So let's move toward that. Again, this is the beam and these are the sections shown and these are the reaction forces are shown. So you have to draw the two vertical lines from the end of the beam in order to draw the shear force and bending moment diagram. So first we will draw the shear force. So between these two lines you have to draw a horizontal line which show you the length across the beam. So at this point, from point A to this is point A, this is point B, this is point C, and this is point D. And distance between A and B is 2.5. From B to C it is 3, and from C to D it is 2 meter. So we have to draw the shear force and bending moment diagram. So from our previous slide, we can see that at point 1 or at point A, there is only shear force minus 20. So you have to take the minus 20 in below this line axis, below, because below force is taken as negative and above force is positive. One more thing is that while you draw the shear force and bending moment diagram, always draw it on the graph paper. And if you do not have the graph paper at the moment, so you can draw the shear force and bending moment diagram by taking the appropriate scale. So on y-axis you can divide it into equal number of parts, and you can say that this one division is equal to, let's say, 1 kilonewton. So definitely you have to draw the divisions on vertical axis, and on the basis of scale you have to take the shear force. So at point A we have a shear force of, or at point 1 we have a shear force of minus 20 kilonewton. So again from point A, and according to your scale, so you will have to plot minus 20 kilonewton. For example, let this point is minus 20 kilonewton. So this is your first point. Now at point 2, so point 2 is approximately at point B, but it is on the left side. So at point 2, we know that at point 2 the shear force is again minus 20. So this is the point 2. Let's say this is point 2, but before this support. So again the shear force is minus 20. So it will be if we join it, it will be a straight line. But if you notice that at point B, we have this left side and right side. So just before the point B and just after the point B. So before the point B, we have 20 kilonewton, and just after the point B, we have shear force 20 kilonewton. So now you have to draw, this is minus 20 and this is plus 26. So again, you have to move it from plus 26. So this is minus 20 kilonewton, and if you draw it plus 26, so let's say this is minus 20, again this is again on the basis of scale you have mark out plus 26. So on that point you will go to the plus 26. So if you join the line, so what does it show you? It is a straight line. It show you, this portion show you that this is just before this point B, and this portion, this from this axis to the upper portion, this shows that just after point B the shear force is changed. Now at point similar, this was a point 3. At point 3 shear force was plus 26. I will show you. At point 4 it is again same as 26. When you calculate it, you will see that V4 will be 26. So again at point 4, so this is the point 4, R section 4, which is approximately at point C. So this point will be the same, plus 26. So again, if you join them, this will be a straight line or constant line. Now at point C, you can see on the left side as well as the right side. So, and on the left side it was 26, and we will see the shear force at point 5. So shear force at point 5 is now minus 14 kilonewton. Clear? So minus 14 kilonewton. So you will have from this point you have to go to minus 14. So this is minus 20. So minus 14 will be somewhere. So if you plot it, so this will be the point or section 5. So you have to join them straight. So this upper portion shows that this is the shear force before this point C, and this is the shear force which is going toward the negative, and that is after point 5. Again, if you are confused how to find this V5 or V4, so definitely you can check that if you section it, so 20 is negative, 46 is positive, so we have 26. Again 26 is upward and 40 is downward, so we will have minus 14. So that why is minus 14. And at similarly at this point section 6, it is also minus 14. So at this is point. So if you join it, so this will give you the shear force. So this is how we draw the shear force diagram. So now we will move toward plotting the bending moment. So for bending moment, again you have to draw a horizontal line between the two ends of the beam, and this axis is show you that the beam length is varies in x direction. So let's start from point 1. So if you look at this, this is the point A is the application of concentrated load. So there is no movement because this force is passing through point A. or you can see that movement at point 1 is equal to 0. So again you have to take the appropriate scale and mark this vertical line as above this axis and below as well, so that you can accurately plot the points at various sections. So let this is point 1. So you can see the movement at point 1 was 0. Now at section 2, so you can see that at section 2 movement was minus 50 kilonewton. So when you draw or when you locate minus 50 kilonewton, so you will have division and according to your scale, and if this point is minus 50, let's say this is minus 50 kilonewton, so at point kilonewton into meter, so at point 2, so point 2 is at this point B, it lies at point B, because we have told you that this point B is so much closer that it is just before the point B, so it is at a distance of 2.5. So at a distance of 2.5 and at point B, so you have to draw the minus 50 kilonewton into meter. Now the question is that we have point 1 and we have point 2. How to join them? You can join them straight, you can join them like this way, you can join them like this way. So how you will know that how we will join these two lines? So let me explain it also. So now you will judge it from using the shear force diagram. So from point A, this was a point A and this is a point B. So from shear force from point A and B, you can see this is a constant line, constant value, or is a constant line with zero slope. So always remember that bending moment equation is 1 degree higher than shear force equation. I will repeat that bending moment equation will be 1 degree higher than shear force. So if shear force is a constant, mean it is a 0 degree equation, so the bending moment will be the first degree equation, and first degree equation gives you a straight line. As this is a constant, so from point 1 to from point A to point B, you can join them in a straight line. Why? Because the shear force is a constant value or 0 degree line having zero slope, so the bending moment is 1 degree higher than shear force. So you can see this is 1 degree equation or linear equation. So if you the linear equation will be, if you plot using linear equation, it will be a straight line. So you can quickly join point A with point B using a straight line. Now at point B, you can see that before point A, which is 2, and after point 2, these movements are same. Clear? So basically this point, this is M2 and it is also equal to M3, and this is minus 40 Newton. Now we will check the moment at point 4. So moment at point 4 is now 28 kilonewton into meter. So definitely you will go toward, you will locate 24 kilonewton. So let this point is 28 kilonewton. So this point is 28 kilonewton into meter. Again, you have to join this point with this point. So you will see the shear force line. So this shear force is a 0 degree line, and again the bending moment line will be a linear. So you can easily join B with point C with a straight line. Now at point C, we have moment at point 4 and 5. We will check moment at 4 and 5. So moment at 4 and 5 are same. So this will be the moment at point C is equal to moment 4 and moment 5, that is equal to 28 kilonewton into meter. Now at point 6, so at point 6 you can see that moment is 0. So if you plot 0, so it will be point this. Again, this is the shear force line or shear force diagram between C and D is a constant line, so it will be up, and it is negative, so definitely it will go toward downward. There will be a downward, so this will come to 0. Again, if it is going from, shear force is going from negative to shear force from negative to positive, and again from positive to negative, so that's why it is, this linear equation is going to upward, and here it is going from positive to negative, so shear force will be downward. So this is how you can find the shear force diagram and bending moment diagram. So now if you look at this shear force diagram and bending moment diagram, you can see that one bending moment is -50, one is 28. So maximum bending moment is, if you take the mod, so maximum bending moment is actually -50 mod, which is equal to 50 kilonewton into meter. Here we are only interested in order to find the maximum bending moment. We are not interested in shear force, and that will be discussed in coming lectures. So from this we get the maximum bending moment. Now we will use, you can see that maximum shear force is 26 kilonewton into meter, and maximum bending moment is 50 kilonewton into meter. So then you have to apply the formula sigma m is equal to maximum divided by S. So what is S? For rectangular beam, we can see that S is equal to, let's say this is B and this is height. So section modulus for rectangular beam is 1/6 into BH square. So you can, if you look at the start of this problem, so B is 80 mm and height is 250 mm. So you have to convert them into meter, because this length is in meter. So for consistent units, you have to convert it into meter. So 1/6 B into H square. So B is 0.080 meter and height is 0.250 whole square, and S section modulus comes out to be 833 into 10 raised to power -6 meter cube. Now you have M, maximum bending moment, that will be at point B, and you can have, you have calculated the section modulus, you will put it and you will have a maximum bending stress, that is sigma m is 60 megapascal or 60 into 10 raised to power 6 pascal. So this is how you will find out the maximum stress in the beam. So in this problem you have seen that shear stress at any section or shear stress is changing along the length of beam. Similarly, the bending moment is also changing along the beam. So we have to find out the maximum bending moment. Once you get the maximum bending moment, you can find out the maximum bending stresses, and further these maximum bending stresses will use to design the beam, that is in next few slides, or that will be discussed in the next few slides. One more thing is that area under the shear force will give you the bending moment. So if you look at from point A to B, so this is the area of shear force. So this is distance, is this vertical distance, this is a rectangular, so you know that rectangular area is B into H. So let's say this is H and this H is -20 and this is B. So -20 is just value, so its height is 20 and this width is 2.5. So if you multiply 20 with 2.5, it will give you 50. So the area under the shear force will give you the bending moment. So this is -50. Now you can see area under this shear force between B and C. So this height is 26, clear, and this length is 3. So if you multiply it, this is 20 and this is 26, clear. So again this is 26. Clear? This is 26. So 26 multiplied by 3 will yield you what? It will yield you the bending moment at in this region. Clear? And see, if you take this region, so you can see this is minus 14 and 2 minus 28. So this is the same as 28. So again the area under the shear force diagram for any section will give you the bending moment. So if you do not know the bending moment at start, so you can also find out for quick finding the value of bending moment. So you can also check that the bending moment in this section AB will be this, bending moment between B and C will be this, and bending moment C and D will be this, and this can be calculated by using the area under the bending moment, shear force diagram.